Welcome back to our look at trigonometric functions and their transformations. At this point, we should have a pretty good grasp of how to change amplitude and how to change the median line. That's by adding a number, irrespectively, right? Adding that number will shift the median line. Multiplying the number after the sign or after a cosine would give us a different amplitude. And that is where we are right now. But that's not the only ways we can change up a function graph. So this is the second part. This is the second goal we have set for ourselves. I want to make a sine function having a different period. Right? Remember, sine normally has period 2 pi, but I want a different period than that. I want a period of, say, 1/4. Not 1/4 pi, not pi over 4, but just 1/4. So I recognize that if I divide 2 pi by 8 pi, that would reduce down to be 1/4, or 0.25. So I know that 8 pi needs to be a factor somewhere. So let's try with the most logical way to apply that. Recognizing I can't divide by 8 pi after I do the sign because that just changes amplitude, maybe I should divide by 8 pi before I take the sign. So let's do sine of x over 8 pi and see how this looks. So here's my sine graph normally. Goes from -1 to 1. Starts at 0 though, sine of 0, 0. Period's 2 pi. But let's try sine of 8 pi. So 1 over 8 pi x, or x over 8 pi. Oh dear. Well, we don't seem to have it, because I would have wanted this thing to go all the way up to 1 and all the way back down to 0, all the way back down to -1, all the way back up. I wanted to have completed the whole cycle before it got to a fourth, or when it got to a fourth. And it's clearly not doing that. In fact, what is it doing? Oh goodness, I am all the way up to 80, it looks like. 78.957, which hopefully is some multiple of pi, but I'm pretty far out there. Right. Oh wait, that's not even a full period, right? That's only half of it. That's going up to down. I need to go back down and back up. I actually have to go closer to 157 to make it all the way back around. Almost 158. Goodness. As a curiosity, just to see, 2 times pi, so 2 times pi, and I think times 8 times pi. Okay. That's giving me the 157.9. See, what happened here is the opposite of what we wanted. If I divided by 8 pi, I did not shorten the period by a factor of 8 pi. I actually I extended the period by a factor of 8 pi. So this did the exact opposite of what I wanted. I wanted to shorten it, instead I lengthened it. So let's kind of stop and figure out why that is. Right? The whole main purpose of why we graph trig functions and do transformations is to be able to stop and parse through how changes are affected. So the function, for instance, is just 2x. So if I were to double all of my inputs before I take sine, that would mean that I'm cycling through twice as quickly as before. Right? So with just y equals sine x, or f of x equaling sine x, when I put 2 pi in, that means I finally go all the way around. But with this function here, if I put x in, if I put pi in for x, that means I will have in this argument still 2 pi. So it only takes half the numbers to go all the way around. So the frequency has doubled. Not the period has doubled when I double this thing. Not the period, the frequency has doubled. Now, frequency we describe as oscillations per second, or cycles per second. So that's hertz, or cycles per minute, or revolutions per minute, RPMs. Those are the units on cycles, or frequency. On the other hand, the time it takes for that one cycle to happen isn't for frequency. That is just period, which is in time, usually minutes or seconds. So for instance, if I do 60 revolutions per minute, or 1 revolution every second, that's my unit, 1 revolution over second. But for the period of that, that's simply 1 second. So there is a difference there, and that difference is one is the reciprocal of the other. So if I have some g of x equaling sine of cx for some number c, what we say directly is the frequency is now c times faster than it was before. Not the period being that much faster, but the frequency. And so, with that in mind, having changed the frequency by that factor, we then change the period by the reciprocal of that factor, right? Those are reciprocals, and so the period is going to be reduced by a factor of c. So for instance, this guy right here, versus y equals sine x, or sine 2x, as compared to sine x, that's going to have a frequency twice as fast as before, so the period is going to be half as much. So the period for this function here would be pi. And the period for what we had before with this one is going to be 16 pi squared. Very, very long time. But I wanted, as I had said already, I wanted 1/4. And so to go from 2 pi to 1/4, I need to divide the period by 8 pi. Which means I need to multiply the frequency by 8 pi. So to get the period I want of 1/4, the function that does that is f of x equals sine 8 pi x. That's going to do it. Let's make sure about that before I say anything too certain. So 8 pi x. I'll have to zoom in again here. And I think this is going to do it. So here's a here's a half. So halfway in between is 1/4. And so yeah, between 0 and 1/4, I have completed a whole cycle. That is how we do it. I know it's a little counterintuitive for many of us. In fact, for pretty much anyone, the first time they look at this is counterintuitive. But the key to remember here is if you want to change the period, that is the reciprocal of having changed the frequency. And this number in here, that thing being multiplied onto the variable inside the argument of your sine or cosine, that is what changes the frequency. If you want more traditional words for this, more general words, not just for sine or cosine, not just for periodic functions, the way you would call this is a horizontal stretch by a factor of 1/c. So if this were a 10, I would be squishing everything in by a factor of 1/10. If it were a big number, that's what it would do. If it were a small number, something less than 1, then I would be pulling everything out. I would be pulling everything apart. And that's what we would have there. And that's pretty much all I need to say about this for now. We'll get into some pretty messy examples in the next video. But for now, let's do a more practical example. Suppose I want to use my function and what I know about functions to model a behavior. So I have a population model I'm trying to create here. I've got researchers following some wolf population in an area. They've been doing it since 2010. And they found that every year, or every month out of every year even, the population had been increasing steadily until about January 2013. It hit its peak of about 1,200 wolves, and then the population started to go down. And it steadily declined for 4 years until January 2017, when it hit the lowest count they ever found of 800 wolves. And then since, it's been increasing ever since. So what I want us to see here is I've got a peak of 1,200, I've got a valley or minimum of 800, and this is all an oscillation. It's gone up, it's gone down, it's going back up again, and we'll assume the pattern holds. We'll assume it keeps increasing again till it hits 1,200 at some appropriate amount, probably 4 years from here. So probably about 2021 is when it should hit 1,200 wolves again. So what we've got is a new amplitude, a new median line, but also we have a new period, right? These aren't 2 pi years apart. These are 4 years apart, and that's only half the period, right? It goes from peak to valley, so it only does half the oscillation in 4 years. I need the period to be 8 years. So what I'm asking us to do here, what we need to do here is we need to make a sine or cosine function, whichever, that has a peak of 1,200, a valley of 800, and a period of 8 years. So let's do exactly that. And the way I usually do this is I do it one step at a time. First thing, I find the period, because that's what happens inside cosine. And then I get the amplitude and the median line correct, because that's what happens outside. So if the period's every 8 years, but cosine has a period of 2 pi, we'd have to divide 2 pi by 8, and we get pi over 4, and that's what I would have to multiply onto cosine here to get what we need. See, period of 2 pi over 4 is 8, and that's our appropriate period. And then we're going to have 200 multiplied on here to go from 1,000 to 1,200, and then 1,000 back down to 800. We're going to shift up 1,000, and our overall function should look like p of t equaling 200 cosine of pi over 4t plus 1,000. Now t, we haven't really established when that starts, but just to make the model as simple as possible, I'm going to set t to be years since 2013. Now, you could do it from any time you wanted, but if you didn't start here, you would have to incorporate yet another transformation, so we're not going to do that quite yet. This is just a model that we're going to use for right now, where t is in years since 2013. And then we could use this model, which is the whole point of creating a model. We can use this model to predict future populations and predict future changes in behavior. So this model would have us guess that in 2018, we would have a wolf population of, well, p of 5, because that's 5 years since 2013, and we would end up with 200 onto negative root 2 over 2 plus 1,000. And if you wanted, you could tell me that the exact wolf population in January 2018 is 1,000 minus 100 root 2 wolves. Please don't tell me that. Please tell me instead how many wolves we should actually have, that number being 859. If you were to actually run this equation, or this expression rather, into a calculator and get the decimal value for wolves, rounding up or rounding down appropriately, you get about 859, 860 wolves. That's what we're looking at, which is up from 60 wolves from the year before, so a little less than a 10% increase, maybe about an 8% increase in population. Not bad. So that's what we got this video. That's what we got for this transformation, how to change period of a function. To change the period, we change the frequency, and the result is the reciprocal of that change. So I have one question for you. Based on all the knowledge you've accumulated so far, not worrying about the function that generates this graph. Actually, we're not quite ready to do that. There's one more change that we'll get to in the next video. But not quite making the equation for this graph. Tell me at least what the period is and what the amplitude is. And that's all we really need to do here. So, given your knowledge of the vocabulary at hand and the graph we have here, what is its period and what is its amplitude? So tell me that, and then I'll see you in the next video where we get into shifting things horizontally, the last change that we have to deal with. So have a good one.